Okay, let's start today's class. Uh, we learned about the branch instructions in the previous class, right? So why do you need branch instructions? So it is because we frequently use a conditional statement in high-level language code, right? So we frequently use if, else, and for, and also we also frequently use iterative loops like for loop or while loop. So actually you can find that these conditional statement or iterative loops include some conditions. So based on the conditions, then we can repeat. We can repeat some code also, or we can execute some statement selectively, right? So that's why the RISC-V instructions. A CPU requires branch instructions, okay? And then in the previous class, we learned about the basic block, okay? So I I mentioned that this is a definition of a basic block. So actually, you need memorize, okay? So and then actually the basic block is a very critical for compiler optimization. Okay, so we learned about the branch instructions, and then these branch instructions change program counter, so which means the execution path. So if there is no branch instruction, then the instructions are executed from top to bottom sequentially, right? But if there is a branch instruction in the middle of a sequence of instruction, then we don't know which part of instruction can be executed or not. Okay, we don't know. So because the execution path is changed by branch instructions. So which means actually we cannot estimate the next instruction. So we cannot expect, we cannot we cannot know the next instruction if there is a branch instruction. Okay. So, but the basic block, this is the definition of a basic block. So definition means that there is no embedded branches. So except the end of the code. And then there is no branch targets. Okay, what are targets? What is the target of a branch? It's a label, right? So if an assembly code includes a label, then it means the branch can be the label. The label can be the target of a certain branch instruction, right? So the basic blocks, but you can just understand the basic block like this. If the first instruction of basic block is executed, then we can guarantee that the instructions, the instructions within this basic block can be executed sequentially to the last instruction in the basic block. Do you understand? If the first instruction, the top of the basic block is executed, then we can guarantee that inside of the basic block, these instructions can be sequentially executed to the top, to the bottom of the basic block. Okay, so this is the definition. Then why is this important? So it is because actually, in order to improve the performance, a compiler can apply optimization method. Okay, but this optimization can be usually applied inside of a basic block. So optimization is like this. So we can change the order of instructions, right? But this optimization can be actually applied with inside within a basic block. So you can find the optimization. Okay. I believe you can learn about this technique in the compiler course. Okay. But you need to understand. You need to understand the definition of a basic block. Okay. Let's learn about the function calls. So what is a function call? So we frequently use a function in a high-level language code, right? So this is an example. So actually in this example, there are two functions, right? So main function and sum function, right? So main function is a special function, right? So if a binary is executed, then firstly, the main function is called and the main function is executed, right? So this is a special function. So anyway, the inside of the main function, you can find the function call here, right? So a function, this sum function is defined here, right? And then this function is called by main function, okay? So now, I will frequently use these words caller and callee. Okay, so caller is the calling function. So I mentioned that inside of the main function, the main function calls some function. So a main function is a caller of the sum function, right? So caller is calling. So this is the active form, right? So callee is the called function. So because inside of main function, the sum function is called by the main function. So sum is the callee. Okay, so it's the passive form. So usually if the word has the EE, then it represents some passive meaning, right? Like the employee. And the employer or employee. So employer is the someone who pays, okay? And then employee is the someone who are hired or paid, okay? So I frequently use the callee or caller in this in the today's class, okay? So then let's see how a function call is executed. So in the main function, the y is declared here. So it means that this statement can be compiled to the assembly instructions, right? And then you can find the function call, okay? Then what will happen? Firstly, this function, sum function, receives two arguments, right? Two input arguments, so 42 and 7. Okay, 42 and 7 is delivered, so transferred to the function, and then function is called. Okay, then what does that mean? When a function is called, then the codes inside of the called function are executed. Do you understand? So you can find that there are some assembly instructions inside of a function. Then what does that mean? So we want to execute a certain instruction. Then how can we execute a certain instruction? We can change program counter, right? So as I mentioned in the previous class, every instruction has a program counter value. And then I mentioned that a program counter is an address of an instruction, right? And then in order to execute a certain instruction, then we firstly change the program counter mapped to the target instruction. And then using this program counter, we can read the target instruction from the memory, right? Then this instruction can be executed. So it means if a CPU if CPU execute a certain instruction, firstly we can set the program counter of the target instruction. Okay, so you need to understand this. Okay, then function is called. What does that mean? The PC is changed to the first instruction of this function. Do you understand? So when a function is called, then a program needs to execute the instructions inside of a function, right? The instruction. And then in order to execute these instructions, then we need to change PC to the first instruction of the function, right? So what is required? So this is a unconditional jump, right? So there is no condition. So function is just called, right? So we can use the jump instruction here. We just jump to this function. And then when a function completes its operation, right? Then usually in C, there is a return argument, right? So return value. And then the function is complete. So what does that mean? Then what will happen? Then it returns. It returns to the caller, but the very next instruction. The very next instruction is executed. Do you understand? Because that's why in a C, we use return in the last line of a function, right? Return means that the function completes its operation and then it returns the return value to the caller. Okay, so return. So what is required? So I mentioned that when a function is complete, then the very next function, not very next statement, a function. So we need to return to this next line, right? Obviously, right? So it's executed and then done, and then the very next line needs to be executed. So what does that mean? We also change the program count value to this line, this instruction actually, right? So what is required? We can also use the jump, right? But we need to know this return point, okay? So it's like this. If we just transfer to some other world, then if we want to return to the current world, so we need to require return point, right? So it's like this, okay? So when a program returns from a function, then a program requires a return point because we need to know the very next the PC of the very next instruction. So actually, when a jump function is called, the return address. So return address is called the RA. The return address is stored in certain point. Then using the return address, we can return to the very next instruction. Okay. So this is how a function works in a high-level language code, right? So you need to understand this. and then you need to understand how a function works. Function really works in a program. Okay. Okay. Then what is required? Okay. So for the function call, I mentioned that we require jump instruction, but we also need to store return address, because when a function is complete, then the program just execute the very next line of the function call. Okay, so function call is implemented using jump and link, and then this instruction is called the JAL. Okay, so JAL is looks like this. So this is the form of the JAL. So this is the RD, the destination register, and then this is the label. Okay, so it means the immediate value. Okay, so JAL means the jump and link. So it means it jumps to this label. Okay, it jumps to this label because we need to call a function. So which means that we need to jump to the first instruction, of the function, right? It jump. And as I mentioned, so we need to store the return address, right? Return point. So the PC plus 4. What is PC plus 4? The PC is the current PC, the PC of this instruction. And then what is PC plus 4? The next instruction, right? Because as I mentioned, the size of a single RISC-V instruction is 4 byte. And then the address is the byte address. So which means the next instruction of this JAL has the PC plus 4 as their PC. So PC plus 4 is stored in this destination register. Usually we use the RA. So it means the return address. Okay. Then function return. And then function return, in order to implement the return from a function, then we require jump and link register. It looks like the JALR. Actually, the JALR looks like RD, destination register, and then immediate number, and then RS, the source register. But usually for the return function, we implement the return like this. So what does that mean? So this is the RD, and then this is the 0RA. So actually RD is the same. So we just store the PC plus 4 in the RD, right? It's a JALR. Okay, it's just, this part is just different, right? But as you can see in this example, the destination is x0. What does that mean? X0 has always 0 value, so it is not updated. So if RD is x0 or 0, then it means nothing. Okay, the destination is not updated. Okay, so it is because when we return from a function, so we don't need to store the return address, right? And then you can find the 0RA. So what does that mean? It means PC becomes the RA plus 0. Okay. And so actually I mentioned that when a function is called, then the return address is stored in the RA. Then what does that mean? And then in this example, RA has the PC plus 4 of this JAL, right? The next instruction. Then this value is PC plus 4 plus 0 is calculated here. And then we jump to this point. So what does that mean? It jumps to the very next instruction of this JAL. Okay? So that's why it's return. Okay? So in order to so this is an example. So in order to implement a function call, the RISC-V supports the jump and link instruction, and then jump and link register instruction. Okay. Okay, let's see the example. So this is the simple example, and then it's just return. Okay. And then this is the right side shows the compiled RISC-V instructions. So this is, so you can find the JAL here, and then this is the program counter of this JAL. So you can find the function call here. So, you know, this is the JAL, RA, and simple. So this is the label of, you can find the label of this function, right? So what does that mean? So in a main function, the simple function is called. Okay, so we can implement this function code using JAL. Okay, so and then you can find the RA. So this is the RD, destination register, and then simple. This is the target of this jump and link. So because the PC of this instruction is 0x300, okay, then what is stored? RA stores the PC plus 4. Then it's the 304. 304 is stored in RA. Okay. And then it jumps to the simple. The PC the label just indicates this 51C. So it jumps to this point. Okay. Then what is the first instruction? The first instruction of simple is just return, as you can see. Okay. So and then it's a return, the JALR 0 and 0 RA. So you know this is the X0, right? So then based on the definition, right? So we need to store the PC plus 4. The PC of this JALR is the 51C. So it 51C plus 4 needs to be stored, but it's 0. So actually it's not stored. Do you understand? And then this is using this one, the source register plus immediate value, we can calculate the return address. So the PC of this jump. So what is the RA? RA has the 304. So 304 plus 0. So it's becomes a 304, right? 0x304. Then it returns this PC. Jump this one. So it executes the add S0, S1, S2, A equal B plus C. Okay, so this is the example, and then this is function call. So we can implement a function call like this. Okay. Okay, but this is just the convention because the function call just function is just also a group of instructions, right? And then as you can see, then usually when a function is called, then we also transfer input arguments, the arguments to functions, right? So which means that these arguments need to be transferred to the function, okay? So this is the some convention, the function called convention. So caller. So when of the caller is the some code, some it's also function, but caller will calls of target function, right? Then it passes arguments, so input arguments to callee, and then usually RISC-V uses register A0 to A7. Okay, so you can find that this is the argument. Okay, A means the argument. So using the A0 and A7, then caller transfers arguments to callee. Okay, and then jumps to callee. So return address is stored, and then callee. And then we jump to the instruction, the first instruction inside of a function, right? Then it performs the function and then returns a result to caller. Okay. So as you can see, you can return some result, and then when a value is returned to caller, then RISC-V uses A0. Okay, so return value, the result of a function is stored in A0 and then returns to the point of call. Okay, and then this is important. Must not overwrite registers or memory needed by caller. Okay, so what does that mean? I will show. Okay, okay. This is the example of input arguments. Okay, so as you can see, a diff of thumbs receives 4 arguments from a caller, and then this function. These statements are executed inside of a function. So we can write the assembly code like this. So because there are 4 arguments, then we can assign these arguments to A1. So registers A0 to A3, A1, A2, A3, right? So as you can see, 2, 3, 4, 5 are assigned to registers. Then diff of sum is called. Okay, then it jumps to this one, the label, the first line of the function, and then the function executes each operation. Okay, and then so the result is like this. So the final result is here. Okay, S3, right? And then we need to return from a function, right? So it's a return. So in order to return the result value, then S3 is transferred to the A0, right? And then it's return. Okay, return to the very next line. Okay. So this shows how arguments are transferred to a function. Okay, and then how the return value is returned to the caller. Okay, but what's the problem? So this is the main function. Main function may use some registers for storing data, right? So, you know, the RISC-V has a 32 general purpose register. So these are integer registers. And then the main function may store some data to these registers, right? And then function is called. And then if you see the function code, instructions inside of a function, then you can find that also. And then obviously, these instructions update update the registers. And what's the problem? The problem is, so for example, main function has some important value in S3, right? And then this value will be used later. But what's the problem? The function is executed and then function override S3 using T0 plus T1. Then problem is that the data in S3 is lost. It's gone. Okay, that's the problem. Then what do we do? It's like a swap. Okay, so A swap B. So how can you implement this? Actually, in order to implement this swap of two values, that we require temporary variable. It means temporary storage, right? Because we store data in the storage, right? It's actually memory, right? So because a function can override register values, then then we require temporary space for storing these values. And then this temporary space is called stack. Okay. So if in this example, if of sums override three registers, the T0, T1, S3, right? And then actually A0 is used for arguments. And then so we can use the actually if of sum can use the A0 because these are argument. So input if these value input arguments are transferred to a function, then these arguments will not be used again. Okay, usually. So it's okay. But T0, T1, S3, these registers are overwritten by a function. What does that mean? If these values needs to be stored in the temporary storage space. Okay, and then this is called a stack. But actually stack exists in memory. So, so when we learned about the memory instructions, okay, and then when we learned about some instructions executed by a CPU, these instructions can only change the registers and data in memory, right? And then we cannot use the registers, right? Because we want store registers in temporary space. So we need to store these values in memory. But we just manage this memory space as stack, okay? Because this memory space is a temporary space, okay? Temporarily used, okay? And this space is called a stack, okay? So then what is stack? Why is a stack? So stack, so just think like the dishes, okay? When we put dishes on the plate, then firstly we put a certain dish and then again and again and again. Then when we use this dish, then we can use the top of this pile of dishes, right? So what does that mean? Lastly input data is used first. This is called the last in, first out. Okay, you can understand the stack like this. So we can just store the data like the stack of dishes. Then when we restore this data from a stack, then we firstly use the top of the stack, the data in the top of the stack, and again and again. Okay, so stack is the memory used to temporarily save variables. So it's a temporary space. Temporary stack is used for storing data temporarily. Okay, and then like a stack of this is it works like last in first out. So like for Q, the last in first out. Okay, so actually some CISC instructions also have the stack management instructions such as push and pop. Okay, so we actually when we manage the data in a stack, then we also use the push or pop. Okay, but in RISC-V there is no push or pop. Okay, so the push means that a new data is stored in the stack. Then the stack size is increased, right? So the firstly, the stack has this data one, and then if the new data, the data two is stored in the stack, then firstly we expand the size of a stack. Okay, then we store this data on the top of the stack, and then push, 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 push. Then a new data is stored in the stack. Then stack size is increased, and then we just store the latest data on the top of the stack. So when this data is used, okay, so it means that it's restored. Then we just pop the pop the top of the stack. So which means we just remove the data in the top of the stack, and then this data is restored from stack. Okay, then stack size is reduced. Okay, the stack works like this. So stack is managed like this. Okay, so which means so this data is stored in the memory, so temporary space. Then if the new data is updated, so it means that a new data is stored in the stack size is increased. Then what is required? So we need to know this pointer, the location of the top of the stack. Okay, and then when we recover data from a stack, then we just remove the top of the stack, and then the stack size is also reduced. What is required? We need to know the pointer to the top of the stack. Do you understand? So the stack managed like this, but unlike the stack of dishes, so in a RISC-V computer, the stack grows down, so from top to bottom. So let's see maybe it's from here. Where is the memory? Okay, so okay, so I hope some students can remember this. So this is the RISC-V memory map. Okay, and then actually when binary code is launched by operating system, the memory map is assigned to this binary. So it is called a process. And then, so in the memory map, you can find the stack here. So stack point. So stack grows down from top to bottom. So we can just adjust this stack pointer to manage the size of stack. Okay. And then as you can see, you can find this is the dynamic data space. Okay. Then heap is the some dynamically allocated data. And then, so if the stack and heap meets, that is called stack overflow, right? Okay. So So dynamic data. So stack is also dynamic data, but we just handle stack data like the temporary data. So stack pointer. So stack goes down from the top to bottom in the memory map. Okay. The stack space. Stack grows down. So so this is, so as you can see, the stack pointer is pointing the top of the stack. So this is the latest data inside of the stack. Okay. And then new data is allocated in the stack. Then firstly, we adjust the stack pointer, and then based on the stack pointer, we can store data. Okay. So it shows the how stack is increased. So firstly, the stack pointer is here, and then in order to store the two words, okay, two word data, then we just adjust the stack pointer to the this address, and then we store these two words, two word data. Okay, the stack is managed like this. So what is required? We need to know the stack pointer. Okay, so let's come back to this code. So stack. So why did I explain this? Because actually, during the function call, as I mentioned, the register data, if these register data are used later, then these data need to be stored in stack. Okay? It's like this. Oh, this is a certain data. It's a caller has this data A. And then caller called callee. And then this A data can be overwritten by callee. So we need to avoid this. So this data needs to be stored in stack. Right? And then when return to this point, then data is restored from a stack. Okay? So we need to implement this operation for function call. Okay, so in this example, T0, T1, S3 are overwritten by the callee, the function diff of sum. So which means the data in these registers need to be stored in stack because it needs to be preserved. Okay, we cannot erase this one. We cannot overwrite this data because because this data can be used later by caller. Okay, so this register data is to be stored. Okay, so we can write the callee code like this. Okay, so what is different? What are different? So you can find these instructions. So SP is the stack pointer. So I believe stack pointer is the RX2. Okay. So firstly, so in this example, we need to store 3 register data. Okay. And then what is the size of RISC-V 32i? The register size. It's 32-bit, right? Right? It means it's 4 byte. So how much space is it required in order to store 3 registers? 12, right? Because the register has 4 byte data. So stack pointer is adjusted, right? Because we will store the register data in stack. So S3, T0, T1 is stored in this address. Okay, so this is the store word. Okay, and then so we can calculate the address like so SP plus 0, SP plus 4, SP plus 8, right? And then the function instructions are executed, and then it's done. It's complete. We need to return. So before returning to the caller, then the register data are restored from stack. Okay, we can use the load word instruction. Okay, because as I mentioned that the stack exists in memory. Okay, so and then adjust the stack pointer and return. Okay, so then it shows the how the stack changes by this operation. Okay, so this is the first stack pointer, and then stack pointer is changed. So then, as I mentioned, the stack grows down. So that's why we adjust the stack using the negative number, right? Minus 12, minus 12. So stack pointer is changed to its original stack pointer, and then stack pointer is changed to this address minus 12, right? Then store word is executed as 3 data, T0 data, T1 data is stored in the stack. Okay. And then, this data is transferred to the original register. Then stack pointer is also change it to the original value. Okay, so after call. So that's how the stack is managed during the function call. Okay. So actually, so I will skip this one because sometimes this one is so students can be confused because the function can be caller or callee. So then some conventions are different here. So just ignore this page. Okay. So I copied this one from the RISC-V manual, the instruction manual, right? So, but the registers can be preserved in the stack, right? But we can actually, the RISC-V also sets a rule for preserving registers. So which means a certain registers need to be stored by caller, right? Or a certain registers need to be stored by callee. So this is a rule, just a rule. So, so this is the register number, this is the ABI name, and then you can find the saver here. So the return address, so actually it can be confused. So maybe the return address can be stored by caller or callee because the caller can be also callee, okay? So but the return address, so it's managed by caller, and then stack pointer is saved by callee. So which means that if callee wants to store a certain value in the stack pointer, then callee needs to be save the value, the data in stack pointer, the stack. So, okay. Okay. Temporary register. X5 to X7 is the temporary register, called the temporary register. So which means actually if these data is used by caller later, then caller needs to save these registers. Callee does not care about the overwriting to these registers. Okay. So if these register has a certain data which will be used later, then caller needs to save these registers in stack. Then save frame pointer is saved by callee, and then also save the register. So when the saved register is used by callee, then callee needs to save the saved registers. Okay. Argument needs to be saved by caller and then also saved by callee. Temporary, right? Needs to be saved by caller. So it's just a rule. So it means when we design a compiler, the compiler needs to analyze the code, and then compiler assigns registers to instructions, right? So compilers know how the lifetime. So when this register data is used, and then when the this data is no longer used. Okay, but when a function is called, we don't know because we just changed the execution path, right? So, but based on the purpose of registers, then a compiler can make the caller saves the certain register, like the saved registers. No, the temporary registers, and callee needs to save the saved registers if these registers are used by callee. Okay, this is just a rule. Okay, so then based on this rule, this can be changed, right? Why? This is the callee, right? So it's a called function. This function stores also T1 and T0 in stack. But T1 and T0 are temporary registers. So actually, based on this rule, callee does not need to store these registers. Okay, so this is the modified in a code, assembly code. But S3 is the saved register, right? So it means that saved registers need to be saved by callee S3. So in the modified code, then stack is just decreased by 4, okay? We just store S3 register in stack, and then stack is restored here. Okay, it's just the rule. And then in a compiler, compiler just decide which registers are stored in stack or not. Okay. Okay, and then non-if function. So what is non-if function? Let's learn about the non-if function. So in a tree, it's a tree, and then there is a branch, right? And then the last part of the branch is a leaf. Okay. So actually, when a program is executed, then program is executed like this. It's a function call, and then it's the execution path is diverged like this, right? So it looks like a tree. The branches of in the tree. So that's why. So these are branches, and then the last part of the branch is called a leaf, right? The last part is the leaf in a tree. As a non-leaf, it means a function can call other function, right? So we frequently implement our code like this. So some function can call other functions. And what's the problem? The problem is when a main function calls this func1, then main function will use the JAL. Okay, what is JAL? The PC plus 4 is stored in RA because the function 1 is complete, then we need to return. We need to return to this point. But this func1 also will call other function. What's the problem? You can find here. The problem is, oh, it's another JAL. So because by this JAL, RA is updated by new PC. What's the problem? Return address is missing. It's overwritten. Then we cannot come back to this point. Okay, because the return address is overwritten. So what do we do? We need to store what? Store what? Original return address. Okay, we need to preserve. We need to preserve the return point, right? But because this function we also call other function, so we also need to the return address in RA. So the previous value, the previous return address need to be temporarily stored in stack. Okay, do you understand? So a function is a non-if function. So which means that, oh, this function will also call other functions, right? Then we also need to store RA in stack. Okay. Then also people returning to the caller, okay? Then the RA is restored from a stack. Okay. Then using this RA, then the return, we can this return from this function. Do you understand? So just to remember, so we need to store RA, the return address. Okay, and then so if a function calls the other function, then return address will be overwritten, right? And in order to avoid this, we need to store this return address in the stack, the temporary space. Then before returning to the caller, then return address needs to be restored. Okay, this is how non-if function works. Okay, so this is the example. Okay, so this is the non-if function. So the stack pointer is adjusted, and then RA is also stored, because compiler can know this function will call other function, the JAL. Okay, then so it will call other function here. Okay, but this is the lib function. Lib function does not need to store RA, right? Because it can just return to its caller. Okay. So, and then before returning to the caller of this F1, then we need to just restore. Okay, restore array. Okay, from stack. And then using this array, then we can return. Okay. So because so sometimes this can be tricky, because the data can exist in register. Also, the data can exist in stack. It means memory. Okay. So, and then, but it is required, because, you know, the register size, the register number is limited. Actually, there are only 32 registers in RISC-V. So we cannot store every data in registers. So it means some data needs to be stored in memory, and then stack is also in memory. The temporary data also needs to be stored in stack. Okay. So this is this slide how the stack is managed, right? From the previous example. Okay, stack point array is here. And then after call F2, then also you can find that the F2 also adjusts the stack pointer, right? Because the F2 also stores a certain data, the data in S4 in stack. So stack pointer is adjusted, and then the S4 is stored here. And then when the returning from a F2, then stack pointer is adjusted, S2, and then S4 is restored, and then return to the on the caller, then the stack pointer is adjusted, and then these register data are recovered. Okay, so the summary. Okay, function call summary, caller. So before calling a certain function, a caller needs to save required. So any needed registers. Okay, it depends on the usage. So it means if these register data are used later, then we need to store this data, right? We need to save this data, right? So save any needed registers in stack. Okay, so for example, array or temporary data, also argument data. If argument data has a certain data which will be used later, then these arguments data also needs to be saved by caller. Then put input arguments to A0 to A7, and then call a function. So this is the call. Okay. And then the call is called. Okay. Then callee save registers, then might be disturbed. So which means that if these registers, for example, the data in saved registers are overwritten by callee, then these register data need to be stored. This is saved in stack. And then perform function, put result in A0. Okay, it's a return value. And then restore registers. Okay, the data in stack is restored to registers, and then return. So the return from callee, then check the return value from callee, the caller, and then restore any saved register. Okay, that's how a function call works. Okay, so it may be tricky because until people jump in like branch instructions, we just assume that the instructions are just executed from top to bottom sequentially, and then also instructions are very simple, but the branch instruction, the execution path, we can just change the execution path. Also, we need when in the for the function call, we need to save some data in stack, and also we need to manage the stack space. So that's why. So this part can be a little bit trickier than some other parts. But you need to understand. You need to understand how this part works. But the function call works in CPU. Also, usually I ask questions in this part during midterm, right? It's a function call. Okay. Okay, we have only 5 minutes. Okay. Okay, so this is the summary of a function call, and then I briefly explain about the recursive function. The recursive function. So recursive function means that a function that calls itself. Okay. So for example, the F1, inside the F1 is called. Okay, so this is the recursive function. Then how can we translate this recursive function in RISC-V? actually we can translate this C code like the normal function, right? So this is the example of a recursive function. It's a factorial, right? Factorial is the n equal n multiplied by n minus 1, multiplied by n minus 2, multiplied by 1, okay, n factorial. And then we can implement n factorial, the factorial function like this. If n is less than 1 or equal to 1, then so just return 1. And then else, we just perform n multiplied by fact n minus 1, right? So this is the recursive function because the fact function, the factorial function calls its own function. Okay, then how can we implement this factorial function? So we can just translate this function like the normal function based on this summary. Okay, so we learned about the function call, and then if a same function, the function is called recursively, so we can just implement the function call like this normal function call. Okay, so it's a temporary is 1, then we just implement this else statement. So no. If this else, then it goes to this part, right? So it just compares this condition, and then if the else condition, then it goes to this part, and then this part will have this function call fact n minus 1, and then so this part is just return 1. So how can you return 1? Simple, because we can put 1 to A0 and return, right? So this is just return, and then else. So in this case, we need to adjust the argument of the function call, right? Call is the fact, right? It's a factorial function. So it just performs the n minus 1 and just call. So this part is implemented. The one has this one, n. It just performs the n multiplied by fact n minus 1, the return value of fact n minus 1, and then return. So this is the function call. So it's a recursive function. Okay, we can just start from this one. The problem is that n was overwritten. Okay, the argument is overwritten because we just adjust the argument to the fact n minus 1 or fact n minus 1, but argument is just overwritten. So what does that mean? We need to store arguments, okay, in stack. Okay, so this part is stored. Okay, so inserted. So actually, in the recursive function, we can just implement the recursive function like the normal function, but we need to manage stacks, okay, for this recursive function. Okay, so I hope everyone can read this code. Then I will explain in the next class. Okay. Okay. Thank you for your attention. See you in the next class. 감사합니다.